In this lesson, we will learn RSA with a complete walkthrough, key generation, encryption, decryption, and a clean proof that decryption recovers the original message. Conceptually, the public key is like a key for locking, and the private key unlocks. We will also track a message as an envelope. Step 1. Key generation. We pick two distinct primes. For our example, choose P equals 61 and Q equals 53. Then compute N equals P times Q, giving N equals 3,233. Next, compute phi of N equals P minus 1 times Q minus 1, which is 60 times 52, equals 3,120. Now choose a public exponent E with E relatively prime to phi of N. Let E be 17. Its greatest common divisor with 3,120 is 1. Finally, compute D as the inverse of E modulo phi of N. That means D times E is congruent to 1 mod 3,120. We get D equals 2,753. So the public key is the pair N, E, and the private key is N, D. Step 2. Encryption. We represent a message, M, as an integer between 0 and N minus 1. In our example, take M equals 65. To encrypt, compute C equals M to the E mod N. We will do fast exponentiation using repeated squaring to compute 65 to the 17th mod 3,233. Watch the steps. After these steps, the ciphertext is C equals 2,790. Step 3. Decryption. Given the ciphertext C, we compute M prime equals C to the D mod N using our numbers. That is 2,790 raised to 2,753 mod 3,233. Fast modular exponentiation yields M prime equals 65, which matches the original message. Now the proof that decryption recovers the original message. We must show M to the power ED is congruent to M mod N for every message M from 0 up to N minus 1. Since ED equals 1 plus K times phi of N, we can write M to the ED equals M times the quantity M to the phi of N, all to the K. We prove this modulo P and modulo Q separately, then combine using the Chinese remainder theorem. First, modulo P. If P does not divide M, then by Euler's theorem, M to the P minus 1 is congruent to 1 mod P. Therefore, M to the phi of N equals M to the quantity P minus 1 times Q minus 1, which is the power of P minus 1 raised to Q minus 1, so it is 1 mod P. If P does divide M, then M is congruent to 0 mod P, and M to the ED is also 0 mod P. In either case, M to the ED is congruent to M modulo P. Next, modulo Q, the exact same reasoning applies. Thus, M to the ED is congruent to M modulo Q as well. Finally, by the Chinese remainder theorem, if two integers are equal modulo P and modulo Q, then they are equal modulo N equals P times Q. Therefore, M to the ED is congruent to M modulo N. This proves that decrypting C equals M to the E by raising to D always returns M. As a final visual check, encrypt the envelope with the public key to get ciphertext, then decrypt with the private key to get back the original envelope. Summary. 1. Generate keys with N equals P times Q, choose E coprime to phi of N, and compute D as the modular inverse of E. 2. Encrypt by C equals M to the E mod N. 3. Decrypt by M prime equals C to the D mod N. For correctness follows from Euler's theorem modulo each prime factor and the Chinese remainder theorem.